When we were working with optimization problems where we didn't have a constraint, we would work out our second order total differential, and we would find that it would be in this form that we see here. All right, then using slightly different notation, so instead of fxx and dx squared, for example, we would use u, v, a, b, h, and q, and we would re-express this second order total differential using this notation here. Then using this notation, we would then set out the Hessian, which was then used to work out if we had a minimum or maximum. Now, with constrained optimization, which we are focusing on in this topic, and by making use of the Lagrangian function, we can show that the second order total differential can be expressed as follows. Okay, so we're not going to go through this entire calculation, but we can take it as a given at this point that the second order total differential working with constrained optimization will look like this. Okay, zxx, zyx, zyy, these are the second derivatives which we can calculate by partially differentiating the derivatives which make up the first order condition. And we'll get to an example of this shortly. All right, so what we need to remember is a big difference between optimizing without a constraint and optimizing with a constraint is that for constrained optimization, we cannot take dy and dx as both of them being arbitrary changes. Okay, we can take one change as arbitrary. For example, if we take dx as an arbitrary change, then dy has to be taken as dependent on dx, because remember, x and y under constrained optimization, these variables are linked, and together they must satisfy the constraint. If we want to put this another way, we can say that we are concerned with the sign definiteness of d to z, not for all possible values of dx and dy, but only for the values of dx and dy that satisfy the constraint. Okay, so let's think a bit about the constraint as it's set out here. Okay, gx times dx plus gy times dy equals 0. All right, so if we think of the constraint in its original form, we will have g as a function of x and y equal to c. And remember, c will be a constant value. All right, so in light of our constraint here, we know that the differential dg must equal the differential dc. Okay, dg must equal dc. Now, dc, if we calculate it, is going to be 0 because, as we said, c is a constant. All right, so the differential dg, which we can work out as follows, is going to be equal to 0. Okay, we need to set dg equal to dc, and we know that dc will be equal to 0. All right, so by rearranging this here, all right, if we have dy equal to, we can see that it will be minus gx divided by gy times by dx, the differential dx. Okay, So this here is indicating to us or showing us the link between y and x. All right, so going back now to our second order total differential, which we have here, okay, given that it is a quadratic form, all right, we can use the same notation that we were using when we were optimizing without a constraint. Okay, so we have d to z in quadratic as a quadratic form, so we can use this notation again. All right, but things are different, remember, because we now have our constraint to work with, and we know that x and y are subject to a constraint, all right? And looking at our constraint here, we can also change the way that we express it, all right? If we use alpha to indicate gx here, and we use beta to indicate the gy here, all right? dx and dy, we are still setting those equal to u and v. Okay, so we've still got u and v here. All right. But what we can now do is, by rearranging this here, we can set it out as v equal to, and taking everything else across to the other side, we'll end up with this expression here, which is nothing other than what we worked out up here. All right, we've got v equal to dy, u equal to dx, alpha is now this partial gx, and beta this partial gy. Okay, and now what we can do is we can rewrite q. Okay, this is our q here, which is indicating our second order total differential, d to z. Okay, we can rewrite this as the function of only one variable. Okay, because we have now got v equal to this expression here, which includes u. All right, so wherever we see v here, all right, we can substitute in what we have on this side. Okay, so that is what we are seeing in this line here. Okay, we're substituting in for v, and then by rearranging, we end up with what we have in this final line here. All right, so don't forget now that q is nothing other than our second order total differential. All right, and we want to know something, we want to know the sign of d to z, so we want to know the sign of q, because that will then tell us whether we have a minimum or a maximum. All right, so looking now at what we have on the right hand side, okay, we've got u divided by beta, but that's squared. Okay, so that's always going to be positive. All right, so ultimately we need to know something about the sign of what we have here in the brackets, because that will tell us what the sign of q is.